Hi, everyone. How many of you write error-free code? These are the folks who do not write JavaScript. JavaScript in the web is the most hostile development environment imaginable. We have a language to start with that has a lot of rough edges that are well documented. And we take that language and we deploy it into a browser that we don't control and has slight performance and behavior differences. And we deliver that JavaScript over networks that are often unreliable and slow. And so we're left with an inevitable consequence that JavaScript apps tend to have lots and lots of bugs. This talk is squashing those bugs. My name is Todd Gardner, and what we're going to do today is we're going to do a live debugging session. I have an app that I've built that I want to show you today, and then we're going to work through 5 different kinds of bugs in that app together using the real tools that you would use today in a web development environment. Does that sound good? Is that hopefully what you were expecting out of this? Awesome. How many of you use Twitter? Yeah, I use Twitter far too much. Twitter has one big problem that this comic perfectly lays out. Twitter is full of people who are wrong. It doesn't matter what side of the issue you're on, there's a whole group of people on the other side of it, and Twitter is all about giving you a platform to correct them. And I think that is really the downside, the downfall of what Twitter is going to be. And so I'm thinking I'm going to launch a competitor to Twitter called GetRanter. Now, are you ready to see GetRanter? Does everybody have like their non-disclosure agreements? This is a brand new app. This is GetRanter. It's kind of like Twitter. So this is my profile on GetRanter. It's got your profile picture in the upper corner. There's a picture of me back when I had more hair on the top of my head. And I've been ranting since June 2015. It's got a timeline of all the different things you've ranted about. I tend to complain about politics and the web and bad JavaScript and all kinds of stuff. And I have an awesome monetization model in place. You can see these ads have been tracking me all over the internet, and they're really targeted. It knows that I'm interested in bacon and Crocodile Dundee and David Hasselhoff. But GetRanter leaves off that most annoying part of Twitter, other people. Because GetRanter, it's all about you. Only you can write in your timeline, only you can see your timeline, and no GetRanter user can interact with any other GetRanter user. I think this is really going to make the web better. This is an anti-social network. So we're in stealth mode, but if you want to see the source of any of this, it's all out on GitHub. My name is Todd H. Gardner. It's out there as GetRanter. So let's dig in. Clearly, GetRanter is going to be the next unicorn of Silicon Valley. But unfortunately, GetRanter is written in JavaScript, and so it has several major bugs in it that we are going to solve today. Now, I have a lot of experience fixing bugs. When I'm not working on GetRanter and telling jokes on Twitter, I started a company called Track.js, which does JavaScript error monitoring. This talk is not about Track.js, but it does give me some context. Through Track.js, I've helped fix over 50 billion bugs through our customers. There's some of them. They're below. They're pretty cool companies that I like helping. So let's jump in and start looking at some real bugs. So this is our first bug that came in from our quality assurance team. And they said that, hey, a user in GetRanter can't delete a rant out of their timeline. They try and hit the delete button, and it doesn't work. So let's go about debugging that. There's a nasty looking bug. Let's kill it. So the first thing I actually want to do is, so this account here on GetRanter is my account. It's my dev account. And so like most of our dev accounts, it's full of like all kinds of crappy data that aren't representative of real users. So GetRanter has this capability of impersonating our real users. And I think that's a very valuable way to debug issues in your application, is to pretend to have the ability to interact with your real user accounts. So I'm going to switch to another one of GetRanter's users. Now this is one of our most prolific users who's been in demo mode of GetRanter for some time, and we're really looking forward to the day when we fully steal him away from Twitter altogether, and he exclusively rants in private on GetRanter. But you can see that my advertisements is just on point. Like, it is clearly going to make me a fortune. But let's try and use this real user to try and debug our issue. So the problem is that the user can't delete a rant out of their timeline. So when they try and hit the delete button, nothing happens. Our page is just reloading. So if we open up our Chrome DevTools, this is just the latest version of Google Chrome, and we try and delete this thing again, we notice that we don't even see anything in our console. Nothing is even coming up. But the whole page is like flickering. So part of this issue is that the page is reloading, and so we don't get any of our context. So what I want to turn on here in the Chrome DevTool setting here is I want to preserve the log. This is going to let me see errors that happened in previous sessions of this page. If I reload now, I can see that navigation events will pop in here. So I see that this page navigated back to getranter.com. If I hit delete, we see that we've recorded this error that cannot read property destroy of undefined. And then immediately after that, we did a navigation event. And so first, before we can really dig into this problem, we have to figure out why is this navigation event happening and see if we can remove that. So what I want to do is I'm going to begin navigating into my code directly here from this error and see if I can figure out what's going on. Now, the error tells me certain pieces of information. The error lets me look at, here's the code that broke, and let me trace backwards. But I could also approach this by looking at the user action that started this and trace forwards. And I can do that with Chrome DevTools by using the selector element, and I can interact with the different things on the page, which I imagine many of you have seen before, especially if you're in design, web design, styling, that sort of thing. And you can select the different buttons on the page and see, like, what are they doing. So for example, here is the delete button. You see it's a button with a class JS delete. It's sitting inside of a form. Here's a bunch of styles for it. But outside of the styles, there's some really valuable JavaScript context here. Is we can look at this tab called Event Listeners, and I can point out to me all of the bits of JavaScript that care about events on this button. And I can trace into it from there. So here's a bunch of different events. I have blur, click, error, pop state, submit. Click sounds like what our user action is they're clicking on the delete button. So if I can go into that, I can see here's the different pieces of code that are listening. Now what you'll notice is you'll end up with lots of different listeners in your code that you don't necessarily recognize. You're probably using some JavaScript frameworks like jQuery or Angular or React, and those will tend to litter the DOM with all kinds of events that you don't necessarily care about. However, it will show you some things that are directly into your code. So for example, rant list view is a piece of my code. I recognize that name. And so we can go in here and say, I have a bit of my code that cares about clicks on this div. And I can navigate directly in and take a look at the code in question. So here we have an initialize function. And in this initialize function, we have an event handler. Now this is a jQuery style event handler where it says an element and we do on the event name, which is a very common pattern that a number of different frameworks use. So this is binding a click event onto an element, and then it's using what's called an event delegation pattern, where the event could go off on any number of elements, and so we're checking to make sure that it matches a certain pattern, the JS delete CSS class pattern. If we just go back to the elements, we can confirm that it does in fact exist. There is the JS delete class in it. And then if it matches it, we call some other function to actually do the work of deleting out that rant. But what happens when you issue this click event on a button that's inside of a form? What would be the default behavior of a browser when that happens? It submits. If you put a button inside of a form and you click on that button, the default action is to submit that form. But at no point did we ever tell the browser not to do what it normally wants to do. We just added our own junk on top of it and never stopped the browser's default behavior. And so we need to do that. Go away, Donald. if we decide right here that we are going to take an action on this event, that we're going to do something with this event, we need to tell the browser to not do its default behavior, which is exposed as event.prevent_default. With this in place, we should be able to, let's clear that out, we should be able to try and delete something out of our timeline. The error still is occurring, but notice we are no longer navigating. So we've solved one part of this problem. So let's take a look at the second problem. So this error, cannot read property, destroy of undefined, is a very common kind of error message. I imagine many of you have seen this before. And so let's break down what this means. We're looking at some object, and we're trying to see if there's a property destroy on that object. But it's not destroy that's undefined, it's the object that we're looking at that ends up being undefined. And so let's see if we can figure out where that is. Now, we're going to start from the code side this time, and we're going to look at the stack trace. So the actual stack trace of this error is very uninformative. We just have 2 lines. We have one bit of code that I recognize, this rant list Vue.js, and then a piece of my infrastructure code. But so much of the world of the code that we write in JavaScript is asynchronous. We are telling the browser, here's some code, I want you to execute it later in response to an event that happens. The problem with that is that we don't get the context of what was the code that attached those events earlier in time. We only see what the currently running code is. In recent versions of Chrome, it's introduced by default async stack traces, which are now described here as these italicized breakouts in their more verbose stack traces. So we see that we have rant list Vue.js and some other infrastructure code, but this code was invoked by a call to set timeout. And set timeout was called via this command onDelete in rant list Vue.js line 33. And so in this way, I can trace back and I understand some context that rant list Vue calls onDelete, at some point is calling set timeout, and it blows up inside of it. Let's take a look at the actual code. Here's the onDelete function. Now onDelete, as I said, is calling set timeout. Our async stack trace knows about that. And then we're trying to destroy some things to remove that rant bit from the UI. But I bet some of you have already spotted what the error is here, because this is the most common error in JavaScript. We've lost the context of what this is. We've passed a function into into the browser's API by set timeout to execute later. And when later happens, the value of this isn't what we think it is. We can confirm that by attaching breakpoints right here. As a quick aside, in the latest version of Chrome, they've actually introduced this multi-line breakpoint thing. You can see it here on this line. I can either break when we're evaluating this.model or this.model.destroy, which is pretty cool. But so with this breakpoint on, let's try and delete it again. And so when we're broke at this particular point, the expectation of this code is that this is this object, this rant list view object that we're working on. But if we actually inspect what the value of this is, it's window, because the browser doesn't know what else it should be. We passed a callback in to execute later, and that point doesn't have context back to the original function. So what we need to do is we need to glue what the value of this should be when this executes. And so there's a couple of different ways we could do that. The first, and probably most compatible, is just to save what you want the context of this to be in your own closure so that you can reference it later. And then depending on which JavaScript book you might have read first, you're going to call that variable either that or self. And it doesn't matter at all which. But you can save the value of this into your own variable that has its own lifetime. And then you can reference that.model.delete and that.remove later. Now let's just save this and make sure that that solution works. Hey, we can delete rants. Now, this is the most compatible solution. This will work back to basically every version of every browser. But if we want to be newer, cooler, trendier JavaScript, we got some other options for how to solve this. The first would be, rather than saving the value of this out into our own closure, is we could just bind what do we want the value of this to be when the function executes later. And so in browsers after Internet Explorer 10, we have this function called bind that is on every function. And we can take a function and we can bind what we want the value of this to be when it runs. Doesn't matter when it runs, how many times it runs. We can bind what we want the value of this to be now and forever. And so by calling bind this on the function here, we're saying the value of this outside of set timeout will continue to be the value of this inside of set timeout. Let's just prove that that works. And we're still able to delete. We have one more way if we wanted to be like really bleeding edge trendy, like only works in like Chrome and latest Firefox trendy. We could drop the bind, and rather than declaring this as a full-fledged function, we could define this as an arrow function, which looks like this. What that lets us do is it lets us define a function like a subset of the capability of a function that has some behavior built into it. First, that the value of this is inherently bound to its outer scope. This is essentially the same syntax, or it's not the same syntax. It's essentially the same behavior as the other model, where the value of this is always what it is in the outer scope. But this is only going to work in Chrome. But if we reload this thing and try and delete, we should still be good to go. Now, I'm only going to really work on latest Chrome right now, so I'm going to just leave this here as it is. Because, who wouldn't just be running latest Chrome, right? All right. I'm going to turn all of those things I turned on off. So this was our first bug. This was a logical bug. And there are two parts to this. First, we were intercepting native browser behavior and trying to do JavaScript-y things with it. But we forgot to tell the browser to not do what it wants to do by default, which is submit that form. This is something that you're going to run into a lot, especially if you follow a progressive enhancement approach to building JavaScript on the web, which has tons and tons of advantages, and I recommend you do it. But you always need to be cognizant that the browser wants to do its own behavior, and you may need to stop that from time to time. The second part of the bug was functional context, which is the most common JavaScript issue. So we looked at Keystone users, my Donald user. I encourage all of you to build that into your applications. Have a way to look at real user data when you're debugging. It exposes so many edge cases that you don't know exist. We looked at the DOM inspector and talked about async stack traces. So here we have another bug. This one came in from a user. And this bug is that the user can type in a rant. Let's say you're feeling really long-winded one evening, and you want to type in a whole bunch of text into getRanter, but you're not ready to rant yet. So you come back later. There's a feature in getRanter that we will remember that rant after you come back. And they're saying that it works, but it remembers too much. So let me demonstrate that, and then we'll talk about debugging it. So here's another guy that we need to squash. So let's pretend that we're going to be Donald and to demonstrate this bug. So the bug is we're going to enter a rant in here, something probably particularly untrue and incorrect that we are going to regret and try and delete again later. Something like DevConf PL folks are so rude, food is terrible, fake news, MAGA. And then I decide, you know what, that is not something I should put on the internet, and I'm going to delete it. Well, the problem here is that when Donald comes back later, it remembers it, and it populates it embarrassingly right back into my rant text. I need to figure out why that's happening. So I'm going to use the same approach to debugging that we started with, as I'm going to look at my UI and try and trace which pieces of code care about that text area so that we can figure it out. So I'm going to look at this text area here in the elements panel below. Come on. Here in the elements panel below, we see it's a text area. It's got some placeholder text in it. And then here's all the different things that are listening. So blur, probably not blur, not click. Key up sounds like, hey, that's a bit of JavaScript that's going to run every time the user hits a key in that text area. And there's a bit of my code that I recognize in there, this add rant view JS. So I'm going to go in there, and I'm going to take a look at this function. Here we have an onChange function that is an event handler. It's receiving an event. And what it's doing is it's trying to read out the value from that text area and then put it in a place called local storage. Local storage is one of a handful of ways that we have in the browser to persist data directly in the browser without talking to some external service. If you want to play with that more, that data is all exposed in the application panel of Chrome. In the application panel, we have all kinds of different access to storage. Local storage and session storage are both key value pair storage systems that have different lifetimes. There's more advanced ones in IndexedDB and WebSQL, and many of you will be familiar with cookies. In local storage, we can see that, in fact, the key, the data from our text box is already in our local storage. We have this key called next rant, and it's storing this heinous rant that we want the browser to forget about. So if we go back here and try and figure out, well, why is this happening? Well, so this first line, we have a bit of weird code here. So we're trying to get a variable text, and we're looking at the event object. Now the event, as part of the browser spec, should have a target of like, what was the element that emitted this event? In this case, the text area. We're trying to get the value off of that text area. But because browsers are terrible sometimes, occasionally event.target will not be defined. And so this particular syntax allows us to recover from that, saying if event.target is a thing, we're going to use it. If event.target is not a thing, we're just going to make up a new object just so that we don't fail. And then in order to recover from that, we're going to make sure that text is a truthy value. When you take a JavaScript variable and you put it into a condition, it's going to coerce the value into its Boolean type. This is called truthy and falsiness in JavaScript. There's a handful of falsy types, which are false, null, undefined, not a number, 0, empty string, and there's one other really weird one called document.all. Which is only supported in a handful of browsers anyway. But if it's one of those values, it's going to be coerced to false. If it's anything else, it's going to become true. And so what we're trying to protect here is a value like undefined, where value would not be defined in that case, from ending up in local storage. I imagine we've all seen from time to time the words null, undefined, not a number showing up in a web UI, where it probably wasn't intended. The problem here is what you pointed out, is that one of the values that ends up being false is empty string. If we put a breakpoint here where we're setting this value, and hit delete, we do not trigger anything. Because, I should put a breakpoint here. If we try and delete this, the value of text that we're able to pull out of our event target after deleting everything is empty string. And empty string is a falsy type, and so we don't reset the value in local storage to empty like it should be. And so we're being too generic here in our condition. What we need to do is we need to be a little bit more specific about what we care about. We want text to be a string. Really, if it's any string at all, we're okay saving it. We're just trying to prevent things like null and undefined from getting in there. So we should really just check the type of string. So the type of text should be string. And if it's any of them, we're probably good to go here. So if we try this again, and reload our page, if we delete our rant, the value of text is still empty string, but the type of text is string. And string will equal string, and we will clear this out. Let's just confirm that that all works. And our rant text is no longer remembered. This was another logical bug. And this one came from a misunderstanding of truthy and falsy types. Specifically, that empty string is a falsy type. And if we put it into a situation where we're going to coerce it into a Boolean value, just because it's not false doesn't mean it won't equate to false. And so a good understanding of truthy and falsy values as well will support that. We looked at the Application Storage Explorer, which allows you to interact with all of these different mechanisms of storing things in the browser. And we played around a little bit with breaking the execution of the JavaScript. Here's our third bug. This bug was identified by our monitoring tools. And our monitors had said, hey, you know, our clients are seeing a lot of 400 bad requests as they're interacting with our app. Specifically, to this URL is our clients are saying, hey, you've made 237 posts to /API/rants in the last day. Why is this happening? Why are our users running into this? Some of the things that our monitoring is able to capture is what are the other actions that the user is doing on the page. And so what I'm able to tell is I know that the user is entering 0 characters into this text area and then clicking on a button, and that immediately is followed by this post to API rants that's getting a 400 bad requests. Now, that's a pretty good set of recreation steps that we can now take into our application and try and debug this. So let's try and squash this bug. So if we just open up our console again, and let's follow the same flow that we would expect our user to do. We're going to go to the text area, and we're going to enter 0 characters. Done. Now we're going to hit the submit button. And Chrome indeed tells us that we got a 400 bad requests to /API/rants. Now, Chrome records even AJAXs that come back with a 400 or greater as an error, and will record it here in the console and give us a bunch of great information about it. Now, if you want more information about network requests than just what is being shown here in the console, the network panel gives you tons and tons and tons of great information. If you don't turn this on, probably the most valuable thing to turn on is your ability to filter. With filtering turned on, this is going to let you find the particular request that you're after much quicker. Because most large web pages are going to have hundreds and hundreds of related network requests as part of its normal operation. And so what I want to look for is I want to look for something with /API/rants. And I quickly see that I have these particular requests that are making that call. I can look into it and I can see all kinds of information, the URL, the HTTP method, all those sort of things about what went into it, including the request and the response headers. I can see what data did I send to the server. I can see what data I sent to the server. Here I sent an object with property text empty string, which makes sense based on the user actions that took place. And I can see what the server responded to me. The server nicely responded with an appropriate error message that told me what was wrong with my request. If you're involved in building APIs, please, please, please include error messages in your response bodies if you return bad error codes. It helps debug why are things happening. So we see that we're sending bad data to our API, and our API is saying, no, that's crap, I'm not going to take that, which is exactly what it should do. So our problem is we're not preventing our UI from making invalid calls. So let's see if we can figure out where that's happening to see if we can trace that. Well, the Chrome network tools are going to show us that as well. Now, I can see an entire stack trace of what was my code that made this call by hovering over the initiator part of the network panel. I can also see it directly from my console. Because Chrome records this as an error, it generates a full stack trace of what was the code that was running that led up to this error, to this network request being formed. And I can look through this, especially what you'll notice with a lot of stack traces involving network is especially if you're using any sort of utility libraries like Angular or jQuery to handle the normalization of network requests for you, there's going to be a lot of goo in it that you don't recognize. And just kind of brush through it. Try and find the last bit of your code that was in there that was part of this chain. And so in mine, I see jQuery, I see Backbone, I see add rant view.js. And so it's this line right here. This.collection.create, somewhere under the covers of the framework, is generating an AJAX request. And so here is the part where I need to make a change to add my own client-side validation. So let's take a look at what this function does. This is an onSubmit handler. And onSubmit is taking an event, and it's preventing the default behavior from the browser, which is good. And then we're creating an object. We're creating a rant object. And that rant object has a single property called text. And text just takes whatever value is in the form, even if it's empty string, and puts it in there. And just goes and sends it to the server, like it's nobody's business. What we really need to do is we need to add our own client-side validation here to make sure that the rant object conforms to what we expect it to be. And so all our real only constraint here is that it's an object that contains a non-empty message. So we can add some simple validation here. If there's a rant, and if there is rant.text, then we can do things. And if there's not, we don't have to do things. Oh, I don't want to do that. Now here, we can take advantage of truthy and falsiness to our advantage. So here, we're going to check two things. First, we're going to check that rant itself is a truthy value, which in this case is guaranteed to be because we're declaring it immediately above. We're creating an object. And then we're making sure that rant.text is truthy, which as long as it's what we need to prevent from getting out into our server is an empty string value. And so empty string would be considered falsy, and we wouldn't fall into this condition anymore. So if we save this up, what we should see here is if we try and do the same process again, entering 0 characters and hitting rant, we are no longer making those requests, and we are no longer generating those errors. However, this is a pretty crappy user experience because we've obviously seen that on any given day, we see about 200 people doing this. And so now what they see is that they are hitting the button and the UI is not doing anything at all. It's not giving them any feedback. And so what we should probably consider doing is adding an else condition here and providing some feedback to the user of like, hey, you can't do this yet. Now, we could probably do that, but that's going to take a little while. So instead, I want to take advantage of some of the native behavior of modern browsers to do that for me. So I'm going to take a look at my core index file for getRanter. And here is here is the text area in question. Now, a text area inside of a form gets a whole bunch of new attributes as part of HTML5 that are supported with many of today's modern browsers. One of the most compatible ones is required. Required allows you to add or to decorate text areas and add validation to your client-side forms without having to write any of the code yourself. The browser is going to validate this before even bothering to trigger the submit event on your form. With that in place, what we're going to be able to do, I'm even going to put a breakpoint here in onSubmit. When we try and send this form with 0 characters in it, Chrome is giving the user feedback saying, please fill out this field. It's saying, hey, this is required. You have to do this. The submit event isn't even being triggered yet. Our code, it hasn't even gotten involved yet. And so we can delegate this whole thing to the browser so long as we're OK with the user experience of this is what bad validation messaging is going to look like in Chrome. And it's going to look a little bit different in Firefox and Internet Explorer and Edge and et cetera. But it allows you to do this sort of thing very quickly with very little of your own code involved. This was a validation bug, a data bug. We had a situation where our UI was allowing a certain class of data to be sent to the server, but the server didn't allow it. Most of our applications are going to require user input. And user input does need to be validated on the server every time to protect our systems from bad data. But we probably need to do the same validation on the clients. And that provides a much better user experience and reduces overall errors. What we looked at was we looked at the network inspector, the response previews, and more of the debugger. All right, let's get into a little bit more intense bug. This is a developer bug. I found it while I was working on GetRanter and I was writing some code. And then I noticed that like the Chrome tab started like filling up all of the memory on my MacBook. And the fans started spinning up and I couldn't hear anything anymore. Like the GetRanter page just consumed all of the resources of the machine. And that sounds a lot like a memory bug. So let's see if we can find a memory leak in GetRanter. Many people don't think you have to worry about memory with JavaScript, which is what's led to the current state of the web and browser tabs consuming multiple gigs of memory. But maintaining the memory state of your application is very important, especially if you're going to be rendering bits of the UI client side. There's a couple of different great tools for debugging this in Chrome today. The first one is under the memory tab. And what this lets you do is it lets you take snapshots of the current memory state of your application, and it's useful for debugging certain kinds of things. This third one, this record allocation timeline, is particularly effective. Use this profile type to isolate memory leaks. It says right in the description. So I'm going to start a profile here, and I'm going to let this thing run for a little while to capture what are the kind of tasks, what kind of things are running in the background of GetRanter. And what it's going to capture is periodically there's going to be a bar that's going to shoot up. And if that bar is blue, that means the browser, the application, just requested a bunch of new memory from the operating system. When that bar, if that bar turns gray, it's released that memory back. But the memory that is still blue, the browser is still hanging on to. So now we're out here at like 35 seconds or so, and I can see a pattern. I can see a pattern that about every 10 seconds, GetRanter allocates a new set of memory, and then 10 seconds later, it gives back maybe 30% of it. But it's keeping it from period to period. We can dig in and we can find out a bunch of information about this, actually. So we can zoom in on one of these areas and select, well, what's going on when one of these memory things come up? And it'll even break down, here's all of the objects that Chrome knows about and what's taking in the memory. Now, oftentimes, these are going to be very low-leveled, very detailed, and kind of hard to understand. But we can look at them individually and see if we can get any clues about where should we start looking for a memory leak. So in this case, it thinks the biggest consumer of memory in this time frame is this object called n. I don't know what n is, but we can look at maybe it's not n. It was just n. Maybe there's a bug in Chrome. Who can debug Chrome? There we go. We'll look at this one instead. So we can look at these objects, and we see that this object here has some things in it. It's view 69. It's an element with an HTML div in it. It looks kind of like maybe a backbone view is kind of what it resembles to me, but I can't really tell. What this can also tell us is if we point at an individual object, it can tell us why are we still retaining this object. So this particular instance of n is retained because it's at index 23 of an array. And that array is called children in a particular object. Now, this information isn't really enough by itself. I don't know where to start here. I have a few clues. I see that there's definitely a memory leak because we're grabbing new memory every 10 seconds and never giving it back. But I don't really know why. And so we're going to look at another tool to try and get even further down on this. So the performance tab lets us grab snapshots of all kinds of things that are happening in a different, more graphical sense. And so what we're going to do is I'm going to take a performance profile here, and I'm going to watch kind of the same period and see if I can identify the same pattern in this tool that I saw in the profile. Now, the pattern that we saw in the other one was a new memory allocation about every 10 seconds. And we're seeing something that's creating new objects, and those objects are being retained in an array called children. That's what we know from the profile. And so now that we have about 30 seconds here, let's see if we can identify the same kind of pattern here. Now there's a lot of data. I love this big screen. I can actually like back out a little bit. Normally I have to have this screen like so zoomed in for people to see it. So this page has a lot of data, and I don't want you to be super intimidated by it, because we're going to kind of break it down. Here at the top, we have a timeline that allows you to zoom in on. This is your 10,000-foot view about like what's happening. What is the CPU doing? What's your network doing? What's your memory doing, et cetera. Here at the bottom, we have some line charts that are showing the same kind of thing. It shows us the JS heap size in blue, the number of nodes in green, and the number of JavaScript listeners in gold. And what we can see here is there's one big anomaly here that wasn't reflected in our profile. And we see this major drop right here. And that drop is probably a garbage collection event. Now, it's probably not meaningful to our memory leak problem itself, because we're just trying to line this up with the memory problems that we saw in our profile. But if you look closer, you can see the same pattern emerging here. You can see there's a slight increase in everything right here. And about 10 seconds later, we see another increase. And 10 seconds later, another increase. Now, that's not really enough information, so we need to start zooming in on this. So with the timeline at the top, lets us start focusing in. And we can get smaller and smaller bits of data. Now, as we start zooming in on these particular issues, we see that it's not a single even increase in the number of listeners, or it's not a single increase in memory and node size. It's several of them that are happening in rapid succession. As we keep zooming in here, we can see that we're at a very small time scale. We're at 0.5 millisecond is our ticks here that we're looking at. And now this middle area becomes valuable, because what this is going to show us is it's going to show us what is actually running at each point in time. Now, if we explode this out, we can actually see what is the bits of JavaScript that are running at this point in time. So here's the code that's actually running that is generating these increases in memory. And so we can start looking at it. We see an XHR call. It's a /API/ads. We can go down and watch the entire call stack here and see if we can find a bit of our code that we recognize. Now, I have a bunch of functions called render in my code. And so that kind of stands out to me, is I have a piece of code called render that I want to look at. With that selected, I can see a bunch of information about it, like how long did this function take and where does this function live? Render took 1.4 milliseconds, and it lives in add_list_view.js. So I have a couple of different pointers at this particular file as related to our memory leak. So let's see if we can deduce what's happening here. Here, when we're starting up the add list view, something that jumps out to me is this right here, set interval. Set interval is a way for us to execute a bit of code on a repeated basis, and it's executing every 10 seconds. Every 10 seconds matches the pattern that we were seeing in our profiler. And every 10 seconds, we're running a couple of these functions, this render function. Render function clears out some HTML and then creates a loop and loops over something and calls render add for each thing in it. Let's put a breakpoint here, because if this is really running every 10 seconds, we should be able to just grab a hold of it. So we see this.l.innerHTML contains a bunch of stuff right now. It looks like it contains our ads. I see ads for my golden bathroom and hair club for men. And it zeroes it out by setting its value to empty string. And then we end up here in render add, where we're getting a new advertisement and placing it into the DOM. At the very end here, we're putting it in an array called children. Children was in our profiling problem. We see this array here currently has 147 things in it. There's 147 views. There's 147 bits of advertisements sitting here in this array. every time we create an ad, we're pushing it into children, but we're not getting rid of that array when we zero it out. So put another way, there's 147 pictures of a shirtless Putin sitting in my browser's memory right now, just waiting to be clicked on. And that's really unfortunate. So let's see if we can find a way to let those copies of that image go. So right here, when we're zeroing out the HTML, we can release our references to the views while we're at it. So there's a couple of different ways we can do it. So this .children is an array. So we could zero out the array by simply setting the value to a new array. But we have the overhead of creating a new array, and that doesn't let me show off something cool, which is, how many of you know that you can get the length of an array on the property length? Right? You can figure out how big an array is by calling the length property. How many of you know that that's a settable property? And that I can zero out an array by setting its length to 0. And now, the next time this runs, hopefully, come on, 10 seconds. The next time this runs, there are 3 things in the array, because I must have run it once already. And after setting its length to 0, there are now 0 things in the array. Now, in order to confirm that this is indeed the memory leak, what we would do is we'd go back here to the snapshot and we'd run another one to make sure that we've removed it. But I'm running a little short of time, so I'm going to skip over that and have you trust me that that was the memory leak, and that is how we fixed it. All right, I got one more bug that I want to get into. This is a bug that I believe a lot of you have had. And it's the user complaining, sometimes your page is slow. How many of you have had that bug? Well, so let's see if we can identify why might GetRanter be slow. And so if I go to GetRanter and I load up the page, loads fast to me, works on my machine, done with the bug. No, we can't do that. So I'm running GetRanter locally, I'm on a fast network, I'm on a powerful machine, but most of our users don't have the same class of hardware and network that we do. And so when we're trying to analyze performance problems, it's good to look at, to try and be in the same kind of platform that our users would be in. Chrome gives us some tools for this, so what I can do here is I can run another performance run. Oop, I don't want to do that yet. I can do another performance run here. But what I want to do is I want to change how I'm going to run the performance. I'm going to set my network to be throttled. I want to be on a slow 3G connection. And I want to have, a slower computer. I'm going to have a 10 times slower computer than I have right now, because that's more reflective of what my user was actually going to have. And now what I want to do is I'm going to run another run of performance, the performance tab. And now I'm going to capture how long my page actually takes to load. And you can see that it's obviously quite a bit slower. The page is still crawlingly slow building itself. It's drawing it together, and we can, as it's putting this together, let's zoom in here a little bit. Probably not that far. So what I can actually do here is I can look at any point in time, I can see what did my screen look like for this user who was loading this page. Now, the total page load time for me was 13 seconds. All of the assets that came together on a slower computer, on a slow 3G connection, would take 13 seconds to load GetRanter. Now what I can do is I can look at here all of the different network requests and which ones were actually the slowest, which ones were blocking other ones. I can look at this and understand that, hey, there's a lot of JavaScript coming down. And all that JavaScript is coming down serially. We're using so many different connections that there's these dependencies starting to happen and it's slowing down. We haven't even brought down the JavaScript for our app until almost 11 seconds in. And at 11 seconds, then I can actually start making the request to get the data involved in showing GetRanter. And so using the performance set of tools, we can look at what are the core asset building problems that are slowing down the rendering of our application and understand better why our end users are complaining that our applications are slow. So this was a performance bug. The core problems that we saw here is there's lots of blocking assets, and those assets are quite large. So the performance timeline is a really powerful tool. I encourage you to go out and play with it. It can tell you lots of information about memory leaks, about performance issues, and it can really help you make your web applications quite a bit more performant. Some of the things we did today were with the help of some monitoring that Track.js provides. That's the other project I work on. Track.js grabs like error reports that look like this. That's how we could know things about like what the user was doing and what they were clicking on. We produce all of those kind of reports and roll them up into interesting dashboards so that you know when you need to make an action on them. That's the end of that. If you're interested in knowing more about that, it's out at trackjs.com, or you can talk to me. If you're interested in a longer, more detailed version of this workshop, I have an all-day version of this that I recorded with a group called Front End Masters that has 10 different bugs, all a bunch of exercises, and you can collaboratively go through and solve these bugs on your own. If you go out to frontendmasters.com, there is a debugging course that you can go out and take that from me. This was squashing JavaScript bugs. I hope I helped you I hope I helped show you a few things in the Chrome debugging tools and how you can fix up the your own applications and make a better website. Thanks so much for coming, and I'm happy to chat with you about your particular issues afterwards. Thank you.